Hi, everybody. Welcome to another session of Discrete Optimization Talks Dots. Today, we're really happy to start with Timo Berthold, who's a developer at FICO Express Optimization Suite, or Express Solver Development in particular. He's also a member at ZIB of the Modal Sim Lab. He's a longtime contributor to MIP and MinLP technology. He's been given the dissertation award by the German OR Society. He was a finalist for the Euro Doctoral Dissertation Award as well. We're very much looking forward to hearing about one way that machine learning can be used to help reduce some of those pesky numerical issues we encounter. So the format is as usual. It's going to be about 25 minutes for the talk. Any questions that you have, please write it in the chat. There will be time for 1 or 2 questions after each of the speakers. And then also at 3 p.m. Eastern time, so after both speakers, we're going to have a session of the breakout rooms where people can just hang out and socialize, as well as also ask questions for the speakers in devoted breakout rooms. And in addition, as usual, there's the Discord channel in which you can ask questions of the speakers asynchronously, and throughout the week, they might be able to respond to that. So with all that, Timo, please take it away.
Thanks a lot for the kind introduction, Alex. So you mentioned machine learning for optimization. And so on this topic, there have been quite a few publications in recent years. So that's about 50 papers that I'm aware of, most of them from the last 5 years. And the authors of quite a few of them are in the audience right now. And then there are people like Elias and Alex who will contact people like me at conferences and asked, well, hasn't that totally changed the way that MIP solvers work? And then I start, well, yeah, see, not really, because only very few of these techniques are implemented in general purpose MIP solvers. And why is that? So, okay, first of all, quite a few of them are on specific applications, and who has worked in the field might have noticed that it's hard to get things really working for general MIP. And well, when asked for the reasons, I start hand waving. Well, these are very complex decisions that you take. There are no easy answers. I mean, easy answers even in the way that we don't really know what the correct answer is at a certain moment. So what is the best variable to branch on? That's very hard to tell in a sense, because a very local decision has a huge global impact, and the same rule might not apply at every part of the search tree, for example. Also, there's hopefully very sophisticated rules already in place for a lot of these things. So you're really fighting uphill if you try to introduce a new technology here. And in many cases, we don't even really know what good features are that really relate to the problem that we want to solve. So there's lots of yeah, but involved. And then earlier this year, it crossed my mind that we should try machine learning for scaling. And I got very excited about this, because I thought if this is gonna work for anything, then scaling should be a really good try. And why is that? So first of all, at least in the way that I thought of it, it's really an either or decision that you take. It's a decision that you take once in the beginning of the solve to start with. And at least for our solver, there is pretty much 2 different scaling versions that work well in practice. And on somewhat half of the problem, the one or the other is a bit better. We know some quite meaningful features, and I will talk about this in a minute, that very well relate to the labels that we want to predict there. And also, currently, there was no rule in place. So we left that decision to the users so far. So there was nothing really to compete against, so to say, except for doing either only the one thing or the other thing. Okay, so perfect conditions to start a project on this. And let me first tell about why we want to do this. So Alex mentioned that numerical issues in MIP solvers can be quite annoying, and I guess a few of you have made this experience. Let's look a little bit into this. So yes, numerical stability is a really crucial topic in many applications that we face. I started a blog series on numerics on our community blog with 3 episodes so far, at least one more to follow in the nearby future. And yeah, real-life applications are often very complex, as you know, and they are also often at least somewhat numerically challenging to handle. So how can we see this? About half of the client problems that we have seen in 2019 had at least some mild numeric issues. Doesn't mean that there were big failures or so, but that we could measure that numerics play a role in solving these models and that we have to be careful with them. Second of all, after performance requests where people asked us, hey, can you make the solver solve double the amount of problems in half of the amount of time? Numerical failures are the most common support requests that we are faced with. So people see an unexpected solution status, suddenly an instance goes infeasible where they expected a feasible solution to exist. There are might be inconsistent results if it gets really bad, so you change, do some insignificant change to a model and suddenly the optimal solution changes. Or simply numeric issues also might come in the form of performance issues. For example, the simplex method goes cycling. Yep, and all of that is of course not wanted. And the question is, what can we do about it? So first of all, how can we learn whether, or how can we see whether our model has numeric issues? There's different information that you get on this. First of all, before starting the model, you can look at on the distribution of the coefficients in your matrix, in your objective, in your right-hand side. So Express will provide you with some output like this here. So this is once for the original model that you put into the solver, and on the right-hand side, you see what it is on the pre-solved and scaled model. And you see here for this example, this is, well, really not too bad. So you have like 1 order of magnitude here in the matrix coefficients. That's really good. 3 orders of magnitude in the right-hand side, and bounds still quite good. So I would call everything which is less than 9 orders of magnitude acceptable as a rule of thumb. And here the objective is on the border to this, but so this, from this one, just looking at those numbers, I wouldn't really expect numeric issues to occur. So, and then there's posteriori information. So this is not belonging to the same matrix here. This is from a different example. So after conducting a solve, you will get a report on numerical failures that the solver encountered. So here, these are different kind of failures, and you see how frequently they occur. So this is really bad. If you see such a thing, you should start worrying about the solution process of your problem. So dual failures is typically something that you can accept if there's a small rate like this one, like 1–2% dual failures is not too bad. But if you see the other kind of failures, then yeah, start doing something about this. So also, you can look at the condition number. So a condition number of a matrix provides a bound on how much a small change in the input will affect, or in the right-hand side here, will affect the solution that you get. So if you put a small error in, how much can this error scale up? And the condition number for a square matrix is defined as the norm times the norm of its inverse. And what we do in MIP solving is that we look at the norm of the basis inverse matrix, because that's a square matrix that we have at hand coming out of our dual simplex method. So one purpose here of scaling will be to reduce this condition number, to reduce this error propagation. And in different solvers, you have the option of sampling the condition number. This could then look here as follows. So you get a final report of how many of them were deemed stable, suspicious, unstable, and so on. And you compute something that's called the attention level. And this is a number between 0 and 1, where it is exactly 0 if and only if all of the condition numbers are stable. And it's exactly one if all of them will be in ill-post, and there's a ad hoc formula more or less to compute the ranges in between. So again, so here you see 0.29, and I would call that cumbersome. So an attention level, my rule of thumb is if it's larger than 0.1, there's an issue with the model. So as you have heard from my description, so numerical information here mainly is there to raise awareness. It shows you there might be something going on. So, and what do you need to do then, or what should you do then? Well, first of all, ideally you can adapt your models to become numerically more stable, or you can try to use some non-default controls to prevent these issues to occur in the first place. Okay, entering scaling. So our most common recommendation when our users are facing numerical issues is try scaling equals 16, which is an option that will enable a scaling method called Curtis-Reid scaling. And so what is scaling? Scaling is a widely used preconditioning technique that's used in various kinds of algorithms, not only in MIP solving. And the aim of scaling is to reduce the condition number, as mentioned before, in order to reduce the error propagation, which is exactly what the condition number tries to measure. And that's done to improve the numerical behavior of the algorithms that are run on the system later on, and also to reduce the number of iterations required to solve the problem. That's actually why people started to look into scaling. I think some 50 years ago, there were the first publications by Pomlin, for example, going in this direction. And more precisely, a p-scaling in particular refers to the iterative multiplication of rows and columns by scalars. This is where the name scaling comes from, to reduce the overall, the absolute magnitude of the non-zeros coefficient in the matrix, the right-hand side and the objective, and to also reduce the relative difference of the non-zero coefficients. Both are valid games here. So let's look at a quick example. We have a linear program here. No, sorry, that's not the example yet. As said, scaling multiplies rows and columns to bring coefficients on one scale. Typically, that scale is close to 1. And there are two scaling methods which are very common. The first is what we call standard scaling. Here you divide rows by the largest coefficient, and then you divide the columns by the largest coefficients, and you might repeat that. Or you do Curtis-Reid scaling, and Curtis-Reid scaling takes more of a global view of the problem and solves an optimization problem of its own, where it tries to minimize the least square deviation from one coefficient over the matrix. Okay, little example. So assume you are working from home for 3 months and you're good at woodworking. So you set up your little home business to make either boxes or chess pieces from wood. You want to maximize the profit. You have a limited amount of wood and you have to buy some tools. So this is where a binary decision comes in, whether you do this or not. So this would be the little mixed integer program that you get out of this. And then you see here the coefficient matrix below. Actually, it is a square matrix, so this will also be your basis matrix in the end. So if you look at the unscaled problem, this will be the basis inverse matrix that you get, and the condition number of this is approximately 245. So if you apply standard scaling to this problem, you see that some of the coefficients go over here, but you will stay at the same condition number, so nothing really changed here. But if you look at Curtis-Reid scaling, this scales the problem in a different fashion. And in this case, you will get a much smaller condition number and a much more nicely looking basis inverse matrix. And you already see here that even if all the coefficients are the same in absolute values, that doesn't necessarily need to hold for the condition number. So looking at the ranges of the matrix is, of the coefficients usually is a good proxy to estimate the numerical stability, but it's not guaranteed that these things here don't diverge. Okay, so that's the two different scaling methods that we typically employ. Until the second to last release, we always use standard scaling and only recommended Curtis-Reid scaling to everyone who had numerical issues, more or less. And now we implemented this new approach, learning to scale, after realizing that one fixed method is not always the best. And here we try to use a machine learning model based on a linear regression to predict which features will result in the smallest attention level. So remember the attention level, good measure of numerical performance of the model. So that's our label that we use. And as features, we use the different coefficient distributions that I showed you before. And we trained this on more than 1,000 numerically challenging instances. And this is what we saw then in, on our test set for validation. So the average attention level here, as I said, those are numerically more challenging instances. So it's not surprising that it is in a higher range here. With standard scaling, it was on average more than 0.1, already almost 0.12. So that's what we used to do. If we always do Curtis-Reid scaling, we would land here roughly at 0.09. So Curtis-Reid scaling on average definitely is an improvement for these models over standard scaling. If we had a perfect predictor that always chooses the one of the two that gives the smallest attention level, we would land here at 0.06 roughly. So that's the what we sometimes also call the virtual best solver. And this is where we ended with our learned model. So as you see, that's almost the same as the virtual best. And we were quite happy with this result. Okay, so we obviously achieved our goal of reducing the attention level if we use this model within the solver, but does this also improve the numeric behavior of the solver? And what we found is that we see tremendous improvements in all different kinds of stability criteria that we can come up with. So after using these learning to scale model, we observed on average 64% less dual failures in the model, 67% less primal failures, less singular inverts, less problems that instances that went unexpectedly infeasible, less inconsistent results, less solutions with violations that are outside the thresholds. The only plus that you see here is the number of stable conditions numbers that we observed on average doing a solve. And the average maximum condition number that we observed on average over the instances went down by a whole order of magnitude there. And finally, the attention level, that's what you already saw on the previous slide. So clear improvement with respect to numeric measures. Question is, how does this affect performance? So one may ask, why didn't we apply at least Curtis-Reid scaling in the first place? By default, it seems to be better than standard scaling. And the reason is that Curtis-Reid scaling gives on average a performance degradation, mostly on those problems that would be stable or that are stable also with standard scaling. So we were quite happy to see here that on our MIP performance set, this was performance neutral. However, we saw a 10% performance improvement on our simplex test set, which we were happy to take, of course, and we started a bit wondering about how does this relate, that we don't see an improvement here. And the reason is, well, exactly what I said before. If you always do Curtis-Reid scaling, you would observe a degradation. And why is that? Because if you have these Curtis-Reid scaled problems, you are less likely to cut off a node. You are, so to say, more cautious in the solve. So we would observe more nodes being solved on average, but slightly faster with the simplex algorithm. So on the overall MIP speed, this two effects cancel out. And yeah, so you can control this with a new control. Here you can enable this. And if you were using the scaling control before, this selection here will still override whatever auto scaling would have done. Okay, so conclusion. Timo now likes machine learning for general MIP. And I've come to the conclusion for myself that this works best for categorical decisions like the one that we saw here. If you have an idea what suitable features are and a well-established level, here this was the attention level that connects to those features. Well, and if you're not competing against a rule that has been fine-tuned over decades. More specifically, we introduced here learning to scale, which is a machine learning module to predict a scaling method for MIP and LP solving. It drastically improves the numeric stability of the underlying solver while not deteriorating performance. And it's one of quite a few recent components in Express that address numeric stability. Another few you saw in the beginning of the presentation. So a little bit of an outlook. The next challenge that we would want to look at is learning the attention level itself. So there's two ideas that we have here, learning it, so to say, a posteriori or a priori. And what do I mean by this? So we tried predicting the attention level just from the numeric errors that we observe. And the first results that we got from this are rather discouraging. While a higher attention level generally leads to more numeric errors to clear, there doesn't seem to be a clear relation that we could pin down. And one problem here is that there's a significant amount of zeros. So even though you have a high attention level, you might only observe one type of failure, or you might not even observe actual failures at all, but you just see that there's something going wrong in your final solution, and so on. So we didn't really find a good way so far to aggregate these different kinds of failures. The other thing that we try is to predict the attention level from the matrix scaling itself, so from the features that we also used for learning to scale, and from computing one single condition number from the very initial LP. And the first results that we saw from this are quite promising. We got an accuracy of greater than 95% for predicting whether the attention level will pass that critical threshold of 0.1. And we also saw that you really need to take those different features, both the scaling and the condition number, into account to get such an accuracy. But yeah, that's work in progress. And I'm happy to take any questions.
Thank you very much, Timo. I'm perfect on time. So we have actually plenty of time for questions. And if anybody has any questions, there are two options. One is please write it in the chat. The second option is you can raise your hand in the participants panel, which is under, I think it's somewhere there for you guys. It's under participants and more, maybe. There's a way to raise your hand. I don't see it as a host, actually. Either way, here, there's Matthew, if you want to unmute yourself, or do you want, I can just read it. I guess you can't unmute yourself. Matthew asks, have you tried this for the barrier algorithm?
That's an excellent question. And so yes, I tried, and I didn't see a big impact. And I asked our barrier expert in the team whether he has an explanation for this, and he said, yeah, I mean, theoretically, the barrier should be invariant to scaling, which I mean, practically, because again, of numerics, this might not be the case, but this explains pretty well that there's you don't see a big difference with applying different scaling algorithms and barrier. And yeah, John asked which machine learning technique did you apply, and also good question. So this was a linear regressor here. We also tried a random forest, and I was actually surprised that I didn't find a slide on this in my deck here. So we also tried doing random forest. The result of the random forest was actually a tiny bit better than the one of the linear regressor. We still decided to implement the linear regressor for, well, two reasons. First of all, it's easier to implement, and also it's interpretable, right? So you really see the connections between the different features and the final output. And pretty much it worked more or less out of the box. The main trick that we added there is that that the label that we used was the well, not the attention level, it was the square root difference of the attention level. So we looked at the difference of the attention level. That's what we tried to predict, and we used the square root there to emphasize values that are close to 0, because that's a typical case here.
I actually have a question too, and it seems like here you were learning just between the Curtis-Reid and the standard scaling,
Yes.
but could you also try to learn an option of no scaling? Or maybe a similar kind of question would be, could you identify which are the numerically challenging instances to prevent the degradation that you see from Curtis-Reid scaling on the general MIP data set that you said happened, maybe because some of those instances are not numerically challenging or something like that? I'm not sure.
Mm-hmm. Yes, of course, you could extend this to different other scaling options. We didn't try to do this mainly out of our own experience that, I mean, don't do scaling at all is hardly ever a good choice for our own experience. So the one other thing that we somewhat frequently recommend is that people try scaling before pre-solving instead of doing it only after pre-solving, but we didn't look into this. And there was another question that you were asked that I already forgot about.
It was just, can you identify which are the numerically challenging instances? I mean, it seems like it's easy enough to do it from some of the metrics that you showed already, but because you had said that on the numerically challenging data set, it was helpful, but on the general data set, it was neutral, and the Curtis-Reid has actually had some degradation.
Yes, but I was kind of pairing apples and oranges there, right? So we, of course, on the numerically challenging test set, the numbers that I showed were all with respect to numerics, and for our performance set, I showed the performance numbers. So you would also slightly improve with on the performance set with respect to the numeric measures. The reason that you only see a slight improvement there is that they are actually selected in a way that they hardly have any numeric issues, so there's not so much to improve upon. But yes, the question of identifying numerically challenging instances in the first place, this is what we are looking into here with this learning the attention level project. That's exactly the idea out of this. We want to be able to tell in the beginning, you might want to be careful with this instance, numerical issues might occur.
Got it. Well, thank you very much, Timo. And Timo will be around also after Jean's talk in half an hour for answering some more questions. Sorry, John, your question maybe will be left for that time if you're still able to stick around for that. So with that, let's thank Timo one more time, and we'll go on to Jean. Please switch sharing screens.
Yep. Thanks a lot, and talk to you later, John, and everyone else.